Hey there, and welcome. Ever stop to think about the invisible magic that cooks your dinner, makes a firework burst with color, or even causes an apple to turn brown? Well, you're in the right place, because we are about to pull back the curtain on all of it.
So, let's kick things off with a quick question. Picture it, the incredible burst of a firework, a slice of apple slowly browning on your kitchen counter, and cake batter rising in the oven. They seem totally different, right? But what's the one thing that connects them all?
If you guessed chemical reactions, you are spot on. They're all driven by these amazing processes where substances completely transform into new ones. And the craziest part, it's happening all around us, and even inside of us, every single moment of every day.
Okay, so here's our game plan. Think of this as your personal field guide. First, we're going to learn how to spot a reaction out in the wild. Then, we'll get into the language chemists use to talk about them. We'll cover reactions that build things up and break them down, ones that do a little partner swap, and finally, we'll see how all of this shows up in your day-to-day life.
First things first, how do you even know a reaction is happening? I mean, before you can understand it, you have to be able to see it. So I want you to think of yourself as a chemical detective. You're not just looking at stuff, you're looking for clues that a fundamental change is taking place.
And these are your top 5 clues. Did something just change color out of nowhere? Are there bubbles forming, releasing a gas? Does the test tube suddenly feel hot, or maybe weirdly cold? Or, and this is a cool one, did a solid just appear when you mix 2 clear liquids together? Chemists call that a precipitate. Any of these signs are a dead giveaway.
Okay, so you've spotted the clues. You know a reaction is going down. Now what? Well, now we have to describe it. And to do that, chemists all over the world use a universal language, the chemical equation. It's the perfect way to write down exactly what happened. Now, this language has one huge, unbreakable grammar rule, the law of conservation of mass. It sounds fancy, but it's super simple. All it means is that you can't just create or destroy atoms during a reaction. You can only rearrange them. So whatever atoms you start with, you have to end with, just maybe connected to different partners. And that is precisely why we have to balance equations. You start with the words, simple enough. Then you translate it into chemical symbols. That's your skeletal equation. But wait, look closely. We start with 2 oxygen atoms on the left, but we only have 1 on the right. That breaks our big rule. So we add those big numbers out front, the coefficients, until every atom is accounted for on both sides. Now it's perfectly balanced. Awesome. Now that we're speaking the language, let's open our field guide and start identifying the different species of reactions. We'll start with 2 that are basically polar opposites, reactions that build new things up and reactions that tear them down. It's really intuitive. A combination reaction is just what it sounds like, 2 or more things combined to form one single, more complex product. And decomposition, well, that's the exact reverse. You take one big thing and it breaks apart into smaller, simpler pieces. A perfect, real-world example of combination is just burning coal. You have solid carbon, it combines with oxygen gas from the air, and what do you get? A single new thing, carbon dioxide gas. 2 things become 1. Now, breaking things apart, decomposition, often needs a little kickstart. You have to put some energy in. You can do it with heat, which we call thermal decomposition. You can do it with electricity, which is electrolytic decomposition, or you can even use light, which is called photolytic decomposition.
All right, next up in the guide are the social butterflies of the chemical world. These reactions look a whole lot like dancers swapping partners on a dance floor. It's all about one element taking the place of another.
So in a single displacement reaction, you've got one element basically cutting in and stealing a partner from another compound. But in a double displacement, it's a total free-for-all. 2 couples literally trade partners, forming 2 brand new couples.
But this dance has rules. It's not random. The key is that a more reactive element will always kick out a less reactive one. For example, if you drop a piece of zinc into this blue copper sulfate solution, the more reactive zinc just boots the copper right out. You'd actually see the blue liquid fade away as a new layer of reddish-brown copper metal forms on the zinc. So cool! And for our double swap, check this out. We mix 2 perfectly clear liquids, the sodium and the barium, swap dance partners. But when barium gets together with sulfate, they form barium sulfate, which is an insoluble solid. So bam, a white, powdery precipitate appears out of nowhere.
Okay, our final category is one of the most important in all of chemistry, redox reactions. Now, the name might sound a bit complicated, but it's really just about 2 things, oxidation and reduction, that are like 2 sides of the same coin. You can't have one without the other. They always happen together.
So, how do we keep this straight? The old school definition is easy. Gaining oxygen is oxidation, losing oxygen is reduction. But the more powerful way to think about it is in terms of electrons. And for that, chemists have a fantastic little memory trick, OYL-RIG. Oxidation is loss of electrons. Reduction is gain of electrons. Just remember OYL-RIG, and you've got it.
Let's look at a real example. The copper oxide loses its oxygen atom to become pure copper. Since it lost oxygen, we say it was reduced. At the exact same time, the hydrogen gas swoops in, gains that oxygen, and becomes water. So the hydrogen was oxidized. See? One gets reduced, the other gets oxidized. It's a package deal.
All right, we have identified all these different reaction types in our guide. We've learned the language. So what? Why does this actually matter? Well, it matters because these reactions, especially oxidation, are happening all around us, shaping our world in ways we often take for granted.
You see the downside of oxidation all the time. Corrosion, that's just the slow oxidation of metals. We call it rust when it happens to iron. And rancidity? You know that stale, funky taste from a bag of potato chips that's been open too long? That's the fats and oils in the food oxidizing.
But this is where knowing the chemistry becomes a superpower. We can fight back. To stop rust, we can paint or oil metal to create a barrier against oxygen. To keep our food fresh, we can add antioxidants or even fill a chip bag with unreactive nitrogen gas instead of air. It's all just incredibly smart applied chemistry.
So there you have it. We've gone from spotting the clues of a reaction to understanding the different ways atoms can build up, break down, and swap partners. You are now officially equipped with the basics of the chemist's field guide. So the only real question left is, as you go about the rest of your day, what reactions are you going to spot happening right in front of your eyes?